Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like impact of synchronization, sterilizations and contentions, reductions in communication overhead. Let's get started. Slide 1. Impact of synchronizations, serializations, and contentions. Let's start by understanding what synchronization, serialization, and contention mean and why they are important in high-performance computing (HPC). 1. Synchronization is a mechanism that makes sure multiple threads or processes reach a specific point together before continuing. For example, when using an MPI_barrier, all processes must arrive at the barrier before any of them can proceed. This is essential to avoid data races but can slow down performance if used unnecessarily. 2. Serialization happens when tasks that could be executed in parallel are forced to execute one after another. This limits parallelism and reduces the overall speedup we can achieve through HPC. 3. Contention occurs when two or more processes try to access the same resource, like memory or communication channels, at the same time, causing delays. A common example is when multiple processes attempt to write to a shared variable simultaneously. Now, how do these affect performance? Increased waiting time is common when unnecessary synchronization points are added. Parallel efficiency drops when some tasks are serialized unnecessarily. Higher latency occurs when many processes are fighting for the same resources. Scalability is reduced, meaning adding more processors won't improve performance beyond a point. Load imbalance arises if some processes complete their work earlier and have to wait for others. CPU, GPU underutilization happens when threads are waiting, not computing. Longer total execution time is a direct consequence of all these issues. Deadlocks, situations where processes are stuck waiting for each other, can arise if synchronization is poorly handled. Energy inefficiency, since hardware is underused, power is wasted. Example, if in a parallel matrix addition program, all threads are unnecessarily synchronized after each addition, the program will run much slower than needed. Slide 2. Advantages and disadvantages of synchronization and serialization. Now let's look at the advantages and disadvantages of synchronization and serialization in parallel computing. Advantages. First, correctness and consistency. Synchronization makes sure that when multiple threads access shared data, they do so safely. It prevents race conditions, where two or more threads attempt to write to the same memory location simultaneously. Orderly execution is achieved when tasks that depend on each other are synchronized properly. For distributed systems using message passing, like MPI, synchronization helps in safe communication. Synchronization enables checkpointing, saving the current state of computation, which can be used to resume if a failure occurs. Essential for reduction operations, like calculating the total sum or maximum value across processes. Maintains data integrity, preventing corrupted or inconsistent data. Prevents data corruption, especially when multiple threads access shared memory. Ensures proper task dependencies are honored, like waiting for an input before processing. Disadvantages. Execution time increases when threads are waiting on each other. Causes idle CPU, GPU time, as not all processes are working efficiently. Leads to serialization bottlenecks, where parallel execution slows down. Scalability suffers, making it difficult to use more processes efficiently. Memory contention when too many processes access the same resource. Risk of deadlocks, livelocks if synchronization is not designed properly. Complex program design, making development and maintenance harder. Adds context switching overhead, as threads wait and resume. Throughput reduction, meaning fewer tasks completed in a given time. Example, If every thread waits to acquire a log before updating a shared counter, the program becomes slow due to excessive waiting. Slide 3. Reductions in communication overhead techniques. Let's now move on to reducing communication overhead, which is crucial in distributed systems using MPI or similar libraries. Communication overhead is the time and resource cost involved in exchanging data between processes in a parallel system. If this overhead is high, performance will suffer, even if computation is fast. Techniques to reduce this overhead. 1. Minimizing synchronization points. Only synchronize when absolutely necessary to avoid unnecessary delays. 2. Using non-blocking communication, like MPI_ISend, MPI_IReceive, to allow computation and communication to happen simultaneously. 3. Aggregating small messages into larger ones, reducing the frequency of communication. 4. Data compression, sending compressed data to reduce message size and thus transmission time. 5. Shared memory usage within the same node avoids message passing and reduces overhead. 6. Topology-aware communication, arranging processes close to each other, logically and physically, to minimize communication distance and cost. 7. Load balancing, ensuring all processes have nearly equal amounts of work to avoid some processes waiting for others. 8. Using asynchronous I/O for input and output operations to avoid blocking compute threads. 9. Data partitioning, dividing data smartly to reduce the need for data exchange between processes. Example: instead of each process sending a message after every iteration, aggregate the data and send it once at the end for better performance. Slide 4. Advantages and disadvantages of reducing communication overhead. Finally, let's look at what we gain and what challenges we face when we attempt to reduce communication overhead. Advantages: faster program execution, less waiting means tasks complete sooner. Better network bandwidth usage, as fewer, more efficient messages are sent. Lower latency, delays caused by communication are minimized. Scalability improves, more processes can be used effectively. Energy savings, reduced idle times mean less power wasted. Less network congestion, especially important in large systems. Real-time performance improvements for time-critical applications. Balanced workload, as time is not wasted on communication. Efficient resource usage, CPU, memory, and network are better utilized. Disadvantages: increased programming complexity, as reducing communication often requires careful algorithm design. Difficult debugging, especially when using asynchronous communication. Requires fine-tuning for different systems, reducing portability. Potential memory overhead due to buffering or aggregating messages. Sometimes there is a trade-off between accuracy and speed. Compressing or approximating data may reduce precision. Designing overlapping communication and computation is hard. Risk of data loss or corruption if communication is poorly handled. Needs hardware awareness. Optimization may depend on system architecture. Possibility of logical errors during message aggregation or complex synchronization. Example: imagine a scenario where large datasets are processed. Without optimized communication, the program would spend more time sending data than computing. Reducing communication overhead makes the program efficient and scalable.